Welcome back. I'm Miss Lisa Blackburn, and this is my YouTube channel for everything I want to talk about science and math. And today we're in physical science class talking about chemical reactions. So I think we've finally gotten to the better part of physical science. What we've been doing is okay, but I think it's better from here on out because we get to do reactions, we do solutions, we do pH, then we move to physics where we're working with toys and levers and machines. So it kind of gets the lab, at least I don't know if the material gets better, but the labs get better for sure. So what we're going to talk about is what is a chemical reaction. If I had water and I boiled it and it became steam, is that a chemical reaction? If I boil water and make steam, do you think that's a chemical reaction? No, because it's still H2O. It might be water in the air, but it's still water. Does that make sense? Darrell, you need to be writing down these notes because I give you credit for it. It's the easiest thing you'll ever do in here. There's no math. You just write down what's up here. So write it down. Okay. So, oh wait, let me find my paper here. Let me find my paper. Got so excited about that I could use my other thing that I got too excited there. There it is. I found my paper. All right. So a chemical reaction is a chemical change. Do y'all remember the symbol I showed you for change that we use in science?
Oh, triangle.
It's a triangle. So you can write, if you remember that, you can write that it's a chemical change. A chemical change. One or more substances being changed into something new. The original substance is called the reactants. And y'all should have learned this in 8th grade physical science. Yes, Darrell? How do you spell what? Reactant. R-E-A-C-T-A-N-T-S. Come up here, Darrell. Here you go. Go get it for him. All right. The new substance is called the products. Just like if you're in a factory and you're producing something, it's called the products. Now, what are the evidence that a chemical reaction may have occurred? Sometimes it's tricky. May have happened. We'll say happened. Sometimes it's tricky and you have to really figure it out. So I'm going to do a chemical reaction and I want you to look at it and tell me what the evidence of this chemical reaction is. You ready? Y'all have done this reaction too. Here's a chemical reaction. What are the evidence that a chemical reaction is going on? What do you say? There's a flame. Well, how do you know it's a flame? What's it giving off? Heat and light. What else? How else do I know it's a chemical reaction? The color. There's a color change. The match was green and brown. Now there's black and orange. What else? You in the front can tell some stuff that they can't in the back. What? It smells? Is that what you said? Yes, there's a smell. What else? Look what's going right now. Do you see it? Smoke. Yes, Jade? I'm in the way. Sorry, I'll stand to the side. Y'all didn't get them all yet. There was a smell. Now, those in the front, use your ears. Do you hear it?
Crackling.
A little crackling, a little noise. So we have a sound, we have smoke, we have a color change, we have heat, we have light. Can I think of anything else that we missed? No, the other one, then the gas. I think you got them all. Good job. Oh, let's not catch my book on fire. That'd be bad. All right, so let's list them. Evidence of a chemical change. The first one is a change in heat. Remember how it gave off heat? There are some reactions that take in heat, that they get cold when they happen. Anybody play a sport or you've got it in your first aid kit at home where you've got those cold packs that you break something, you shake it and it gets cold and you put it on your injury? Do y'all know what I'm talking about? that would be something that's a change in heat, but instead of getting hot, it gets cold. Another one that we had was light, and we also had noise. These three are all a change in energy. Big E is energy in science. We also had a color change. And we had smoke, but we're going to call it production of a gas. And sometimes we see that as bubbles. Bubbles would be producing a gas. It wouldn't always be smoke. You could also have, they brought you your thing. And yours is better than mine. It has an Oreo on it. Then you can also have production of a solid, which is usually a white powder, and it's abbreviated PPT for precipitant. So you hear that term on the weather. The weatherman says we're going to have precipitation. What does that mean when he or she says that? What does it mean if we're going to have precipitation on the weather?
It's gonna rain.
It's going to rain or snow. In science class, it's more likely a solid. In science class, it's where we don't usually mix gases and have water come out of it or rain. What we mix are liquids, and then a solid comes out. But it's just a change of phase. So I brought you an experiment to show you this. This is sodium carbonate. Does anybody know what sodium carbonate's common name is? Do you think it's real dangerous? Do you think it's dangerous? Am I dressed like it's dangerous? No, it's this. It's not baking soda, it's washing soda. You add it to your laundry. So you don't usually wear goggles and an apron or tie back long hair when you do your laundry. So I wasn't too worried about it. But I dissolved this washing soda. Anybody ever, if you make your own detergent, you buy this and put it in it. Anybody know somebody who makes their own detergent? I tried it. My detergent was no good when I did it. And the other one I have is calcium chloride. And I'm going to notice they are both clear liquids. And then I'm going to mix them together. I'm going to start with some calcium chloride. And now watch while I add some of the washing soda to it. Ooh. Do you see how it got white and cloudy? This experiment is called Cloud in a Bottle. Kind of a fancy name. Excuse me. So this would be considered a solid precipitant. It got cloudy. It's got a solid in it. If I let this sit long enough, the solid would settle out and it would all go to the bottom. There'd be a white powder on the bottom. So this was I wanted to show you the last one, the production of this solid. These are evidence that a chemical reaction has happened. So, chemical reactions release or absorb energy. Which one do you think is giving off energy? Endothermic or exothermic? Which one sounds like it's giving it off? Exo, because it sounds like the word exit, doesn't it? And exit is to leave. I'm going to exit. I'm going to leave. So endo is to go in. It's sort of, you can hear that in it. Endo. So endo takes in energy. It takes in energy, and exo gives off energy. Gives off energy. An example of endothermic is a cold pack. I'm not only going to do one. See how it says and? Just mark that and out. I don't want to give you the other one. It's too confusing. And exothermic is hot hands. Anybody ever bought hot hands as an impulse item at the gas station in the winter? You break it and you put it in your pocket and it stays warm for like 5 hours or something. So that's one that's exothermic. It gives off heat. Our match did too. We can say our match gave off heat. burning that was giving off heat. Now, fun exothermic facts. That once this reaction happens and it gives off the heat, it's more stable. It's more stable once the reaction happens. The stronger the bond, the more energy is given off. So say, do y'all know what C4 is? Do y'all know what C4 is? It's a bomb. It's an explosive, plastic explosives. So a C4 is makes a big bomb when it goes off. Do you think the bonds in C4 are strong or weak? They're very strong, much stronger than the bonds in my match, which didn't explode at all. So the stronger the bonds, the more energy released. And also the great majority of reactions are exothermic. Most reactions give off heat. There's a few that take it in, but most of them give off heat. There's a few that feel cold, but most give off heat. All right, how do we feel about this? Is this easier than last time? That says great majority. I was running out of room. The great majority are exothermic. Yes, ma'am. Talk louder, I'm deaf. Ah, yes, we need to production of gas or solid, and then we'll do smell. Yep, sometimes you can tell by the smell. Thank you, ma'am. Make sure you get smell on there. Smell, you can smell it. We smelled that chemical reaction. Production of a gas or solid, and then smell. Okay? Y'all let me know when I can scroll. Up. Yes, sir? Endothermic is a cold pack. And then it says and I'm not going to give you the other one because it's confusing. We're just going to say cold packs. That's good enough. Okay, and then any other questions before I scroll? I'm really getting habited to this early release schedule where we're getting lunch early. Like I'm already getting hungry for lunch. How about you guys? Are y'all enjoying these early lunches we've had this week? Except yesterday with the PSAT, y'all didn't get to eat lunch till late.
No, we didn't get to eat at home. Yeah. Some people didn't even eat one.
That is not good. All right, can I scroll now? May I scroll? Okay. All right. Let's go over here to home. Then try to click on this. All right, so our next point is atoms are rearranged in a chemical change. Do you have that in your notes? Yes. Yes? Okay. They must obey the law of conservation of mass and energy. What is the law of conservation of mass and energy? I'll let you have bonus points for knowing it. And we talked about it on the quiz. What is it?
Matter cannot be created or destroyed.
Yes, matter and energy cannot be created or destroyed. So there was a creation. And we know that things were created because they're here now. You are here. You're made out of atoms. So at one point, there had to be a creation of atoms. Does that make sense to you? So there was a point of creation, but ever since then, ever since everything got created, the matter and the energy has never been created or destroyed again. It only changes form from one to another. Does that get in your head? So these atoms that make you up have been around since day one of creation. Isn't that weird? Isn't that weird to think about? Your atoms have been here ever since it all started. That's interesting to think about, isn't it? So we don't know everything about that moment of creation. We don't have a time machine. We have speculations. But we know that matter and energy were created because they're here now. And we know they cannot be created or destroyed now because that's one of our laws of nature. So right now they can only change form from one to another. Got that? I would say any questions. There's lots of questions about that. So, and I probably can't answer them. So we're moving on. All right. So now, we're going to, that's one of our standards we're going to be talking about is this law of conservation. And then the next thing is particles must collide for a chemical reaction to occur. When I struck the match, if I hold the match right here and the box here, is there any danger of my match turning into fire? No. I have to put it together, right? I have to put this chemical and this chemical on this strip together. And do you think it'll light if I just do this? No. I have to really squish it hard to get it to light. I have to force the atoms to touch and to collide, and then I can get my chemical reaction. Now, they used to make strike anywhere matches. They would have this chemical and that chemical together in the match head, and you didn't have to have the box to strike it. You could strike it on the ground. You would see in westerns where cowboys would strike it on their boot. Men would strike it on their beards and go and be able to light a match. You don't see those so much anymore. I thought they totally quit them, but they do still have them. But they're more rare. The reason why is people would leave the box of them in their car or truck on the dashboard in the South in the summer, and what would happen to them? They would catch on fire. They would spontaneously combust and burn up the person's truck or car. So you'd come back and it would be all burnt up. You'd come out of Walmart in your car, you'd had a car fire. So people don't buy those so much anymore. But I remember having a box when I was a kid. I do not advise any of you play with matches. I was a bad kid, I did. And I was a budding chemist. And I had a box of strike anywhere matches. I remember sitting on the curb and just striking them on the street and throwing them down and striking another one and throwing them down. And they were fun. I liked them. All right. So our example is our match. We had to make them collide. Our chemicals was potassium chlorate plus phosphorus is what we added to it. And we got potassium chloride plus phosphorus 4 oxide plus energy. Okay, now, accurate chemical equations. Chemicals are like recipes of how to make chemicals. So like, I mix up chemicals all the time as a chemist, and I follow recipes. But the recipes aren't written like a regular cookbook. They're not like a regular cookbook. A regular cookbook, you list the ingredients, and then you have the instructions underneath. Cooking is chemistry. Cooking is chemistry. Just like my match. This was a chemical change. Would it be easy for me to get my match back again? Could I even get my match back again? With a nice little green top and made out of wood, could I get it back again? No. So a chemical reaction has happened. Cooking is the same thing. Cooking, you can't get your ingredients back again. But normally, we don't write our recipes the same. So what I have here is I've written a recipe like a chemical reaction. Now, this recipe was invented by my old neighbor, Mabel Johnson. It is a very popular recipe now. Mabel entered it in the Pillsbury Bake-Off. Have y'all heard of the Pillsbury Bake-Off competition? She did not win, but she was a runner-up, and so it was published in the cookbook, and since then it's become very, very popular. The next year she did win. She got $100,000 in a new kitchen. But the recipe she won with was weird. She made a recipe for onion cookies, savory cookies to eat with soup. She won. This recipe that everybody loves didn't win. This recipe is really popular. I'm going to scroll it up so you can read it. I'll go back to home. Click. Okay, and it's for peanut butter cookies. And I wrote it like it is a chemical equation. It's 1 cup peanut butter plus 1 cup sugar plus 1 egg plus 1 teaspoon of vanilla makes a batch of, that should be an arrow right there. It makes a batch of peanut butter cookies. If yours is messed up like mine that says A, make that be an arrow right there. It makes a batch of peanut butter cookies. What does this recipe not have for you cook types out there that regular cookie recipes have? Flour. Do you notice how it doesn't have flour? That's why everybody loves it. There's all these people now who can't have gluten. There's all these people who do keto and they try to avoid bread and flour. So people love her peanut butter cookie recipe, and you see it everywhere now. But Mabel, my neighbor, made it up. It was her recipe.
Wait, is she not your neighbor anymore?
No, she moved to Florida.
Why? Because she got all that money?
Well, actually, she moved to Ecuador first. She became a missionary and moved to Ecuador, and then she moved to Florida.
Oh, wow.
Mabel Johnson, Ecuadorian missionary. And she invited me to go visit her when she was in Ecuador, and I never did. I wish I did. Wish I had gone to Ecuador. That'd be interesting. Anybody ever been to Ecuador? No?
Where is that?
South America.
I'm just asking.
All right. So anyway, this is a recipe. Now, what I used to do was I let the kids do this is a makeup assignment. If they had a real bad test, they could make these peanut butter cookies at home, because remember, cooking is chemistry. And I let them bring them to class, and we all shared them, and we talked about how bad some people's cookies were and how good other people's cookies were. I can't do that anymore. Too many of y'all have peanut allergies. I would be killing a kid, wouldn't I? So what I'm doing with my chemistry, though, a lot of them failed the last test, and I told them that if they want to do the makeup assignment, they can make the cookies at home, take a picture of themselves at home with their cookies and their oven in their kitchen, and then they can bring me 3 cookies. They have to write the recipe like a chemical reaction, and they can bring me 3 cookies to class, because I have to make sure they're not store-bought, and I have to make sure that they're not from a tube, that you made them from scratch, and that you really made them and not your mama. That's why it's got to be a picture of you and the oven. Now, and the cookies, you and your cookies. Now, and that way, kids who are allergic to peanut butter can do a different recipe. If you do a different recipe, though, you have to write it. I will let y'all do this. So if you want to drop your lowest test grade at the end, and you can wait, I can wait till I apply it to the very end, you can do the cookie assignment. Does everybody understand the cookie assignment? You have to write the recipe like a chemical reaction. You have to do the chemical reaction, which is make a batch of cookies, share the cookies with your family, but bring me 3 in a Ziploc bag. What else you got? What? Would you make them? They'd have to be written like this and from scratch. So, yeah, it could be something else. As long as you can write it, the point is you have to write it like this. Ingredients on one side, products on the other, amount in front as a big number. Do you understand the qualification? Okay. But this isn't quite enough. So I'm going to have to tell you in the notes a little bit more, because like, how long do we cook them for? What temperature? I'm going to show you that as we get further down in the notes. So if you make cookies, make sure I'll show you how to write that on the recipe too. All right, so with our cookie makeup lab, I'll probably put it in Canvas so you can upload your pictures of you and your cookies through Canvas. But then you have to bring me the cookies too to get credit. All right, where are we now? So, atoms and masses are conserved in a chemical reaction. That means what you put in is what you get out. It can't go away. You can't be the one to create or destroy matter. Can't be done. And the coefficients, the number in front, indicate the amounts. So we have to balance chemical equations, and that's the main point of this test. You're going to be balancing chemical equations. Do y'all remember doing that in middle school? You probably did it. If not, today's a good day to learn it. Okay? So this is how it works. So I have here hydrogen. I'm going to make it look like this. And I've got an oxygen. I'm going to make it look like that. And over here, I have a water. Now, my reaction here is not balanced. I have 2 hydrogens over here, 2 over here, 2 oxygens, but only 1 oxygen there. I've gotten rid of an oxygen. You're not allowed to do that. I can't destroy matter. So that means I have the amounts wrong and I have to change it. I've got to put another water over here so that I have 2 oxygens. I've got to put another hydrogen over here, so I've got 4 hydrogens. How do you feel about that? Do you see how it works in your pictures? You've already got the pictures drawn. Now, these are the rules for balancing chemical equations. You cannot change the subscripts, the little numbers at the bottom, because if you did, you would be changing the chemical. So you're not allowed to change those little numbers at the bottom because you would be changing the chemical. And that would be terrible. Say you're supposed to have water and you change it to peroxide. You could drink water. Drinking peroxide, if it was pure, would kill you. So we can't change the chemicals. You do change the big numbers in front called coefficients. Those are the big numbers in front. The big numbers in front. And you can never insert a number in the middle because that's not allowed either. You have to keep the molecules together. You can't go splitting them. Okay, so let's do an example problem. On this side, here's a reaction. Here are my products. Those are the reactants. The arrow means what you get, what you make. Over here, I have 1 silver. Over here on this side, do you see that little 2? I have 2 silvers. So I have to go back over here and put a 2. Now I have 2 silvers on both sides, but I need to check everything else. I have 2 hydrogens here, 2 here, 1 sulfur here, 1 there. So it is balanced. I can give it a little check now. It's balanced. How do we feel about that? All right. Let's try this one. Over here I have 2 hydrogens. Here I have 2 hydrogens. So far so good. Over here I only have 1 hydrogen and there I have 2. So I have to come back and put a 2 right there. Now my oxygens are good. 2 oxygens, but it messed up my hydrogens. I have 2 times 2, which is 4 hydrogens over here, and over here I only have 2. So I have to put a 2 right there, and now it's balanced. Check. Is it starting to make a little bit of sense? Darrell, wake up. Wake up. I know this is not extremely exciting. Let's try this one. Over here I have 1 sodium. There I have 1 sodium. Here I have 2 chlorines. Here I only have 1. I have to put a 2 in front. That messed up my sodiums. I go back and put a 2 over there. Let's do another one. Here I have 6 carbons. Here I have 1. I need a 6. Here I have 12 hydrogens. Here I only have 2. What times 2 is 12? 6. So I put a 6 there. Now I have 12 hydrogens. And now I'm going to look at my oxygens. I have 6 times 1 is 6. Plus 6 times 2 is 12. 6 plus 12 is 18. Over here I have 6 and 2. So I only have 8. But if I put a 6 right here, I'd have 12 plus 6 is 18. So if there's a plus, you have to remember to add them both up, the 2 sides of it. This will get easier the more we practice it. We're going to do a lot of worksheets practicing this. So don't worry. Tomorrow what you're going to be doing for your digital day is you're going to be doing a thing with ionic and covalent bonds. You're not going to have to do this yet. It's a little computer thing. You answer the questions and you run it off. Let's see if I ran the questions off for you. No. Yeah. You don't have a printer or whatever, you don't have to print it. Just write the answers on a piece of notebook paper. You can print it off Canvas if you want to, or you can just write it off a piece of notebook paper. All right, so we're gonna stop. We gotta do this one. 2 nitrogens, 1 nitrogen. We'll give it a 2. 2 times 3 is 6 hydrogens. What do we multiply times 2 to get 6? 3. So that's that one. Okay, we're going to stop right there, and because we only have like 5 minutes left, and I'm going to double check that I didn't run off your Canvas assignment for you. Like, share, subscribe.